Hi everyone. So in this video, we're going to continue to talk about using the shell method to find the volumes of solids of revolution. And so this video is basically just going to be like 4 different examples, and these examples are each going to bring in something a little different from what we saw in the last video. And so the first thing we're going to be talking about is situations where you have to integrate with respect to y instead of with respect to x. So I just want to quickly remind you of what the shell method is and where it comes from just by looking back at a slide from last time. So the idea behind the shell method is that instead of taking your solid and slicing it into these, discs or washers, because of its round shape, we can instead break it up into these nesting cylinders. And then how do we find the volume? Well, instead of adding up the volume of slices, now we're adding up the volume of these cylinders. And so how do you find the volume of a cylinder? Well, it's approximately going to be equal to 2 pi times the radius times the height times the thickness. And so that's, we have the kind of the cylinder picture, and then this is what it would look like if it was unwound. But either way, you can see that the volume is going to be approximately equal to 2 pi r, which would give you the circumference times the height times the thickness. And so when you go and add up infinitely many of these, that ends up giving you an integral that looks like this. And then when you actually go to integrate it, you can pull out the 2 pi. So, if you're looking for what's a way to kind of memorize this, I would just think about, how do you find the surface area of a cylinder? And that would be 2 pi RH. And then the dx is what adds that thickness to make it into a volume instead of just an area. So this is the setup if you're integrating with respect to x. So I just want to kind of summarize that and then say what's going to be different with integrating with respect to y. So when using the shell method, so if the solid has been revolved about the y-axis, you're going to integrate with respect to x. So basically the variable that you're integrating with respect to is the opposite of the axis, right? And so that was what we just looked at, but let me just write it down again. So that was v is equal to 2 pi times the integral from a to b of the radius times the height dx. And so one thing that's important to note here is that the radius and the height, these are both going to be functions of x when you're integrating with respect to x, right? And then another thing is that the bounds, the a and the b, those are also going to be x values, not y values. Okay, so what about if you're revolving around the x-axis? Well, then it's with respect to y. So if the solid has been revolved about the x-axis, well, then you integrate with respect to y. And the volume formula is going to look like pretty much exactly the same, just with a dy instead of a dx. But what's important to remember is that even though the formula looks like identical, in this case, the radius and the height, those are going to need to be functions of y. And we'll do an example in a moment and we'll see, how that kind of looks. But those need to be functions of y, and then the bounds also need to be y values. Okay, so let's jump right into an example. Okay, so this example says we're going to find the volume of the solid obtained by revolving the region bounded by x is equal to negative y squared plus 5y minus 4, and x is equal to 0 about the x-axis. So it's kind of similar to one of the ones we did in the last video in that we have kind of just the top of a parabola, right? This parabola would continue this way, but we're cutting it off because we also have x is equal to 0. So we're looking at this region here. And by the way, so I just wanted to quickly mention, because I know in these videos, I keep just sort of having the graph already pulled up. I would just say that, for your own practice, for getting ready for tests and quizzes, things like this, things that are like a parabola or a line or square root graph or something like that, I would expect you to know, or like e to the x, I expect you to know how to graph those by hand. If it's something more complicated, like e to the negative x squared, or yesterday we did 1 over 1 plus x squared, I don't expect you to know what those graphs look like, but I would expect you to be able to graph things like this parabola by hand. Okay, so we're revolving this around the x-axis. So what is that going to look like? Well, let me do my best. From the side, it's going to look like this. And again, just like on the last one, I'm not going to really fill this in because I just think it will actually make it look more confusing. But what would this look like? Well, picture you're taking this pink region and you're really kind of swinging it around in a circle. And so this would look similar to what I described in the previous video. This would look like the top half of a donut or a bagel, right? Like you took it and you cut it in half and you just took the top half off. It would be curved on the top but flat on the bottom. Okay, so let's start by drawing a sample cylinder and then we'll go from there. So to draw a sample cylinder, in this case, we want to now go to a specific y value. So I'm just going to kind of pick one. I'm just going to go maybe just a little bit above 2. And then we're going to go symmetrically across onto the other part. And that's going to be the other side of the cylinder. And then we attach them with a circle like this. And then in the bottom, we can make it look rounded as well. And so that would be a sample cylinder. And just to draw a couple more, just to kind of, so you can visualize what's going on, you could also have one around here. And so this would look like this. You could have another one maybe all the way out here. So that would be like there and there. This one's going to be a little bit shorter. So it's not like they always get bigger as they go. It depends on the shape of the graph. So you just have all these different cylinders of different heights and different radii nesting within each other. Okay, so we need to figure out what the radius and the height are. So I'm going to draw first in the radius would be this distance here. And so as you might remember from the last video, in the last video when we were integrating with respect to x, the radius was x. And in this case, the radius is just going to be y. And so why is that? Well, basically because the radius is just equal to the height, right, of where we are. And more importantly, the reason that the radius is just y is because we want to include all of the different possible y values, right? So I just erased them, but we had like a few different cylinders here, and all of those were at different heights. So you can imagine, making another cylinder that's at this height and this height and this height and this height. So all of these different y values are going to need to have a cylinder there. And even everything between those, we want like infinitely many of these cylinders. And so we really want to include every y value. And, of course, there's some y values that aren't going to be included. Like, for example, y is equal to 1/2. There's no cylinder here, right? Because that's like in the middle of the donut. And so how are we going to make sure that we exclude that y value? Well, that's where the bounds will come in. So similar to what happened in the similar example to this in the last video. So the radius is just y. And then what's the height going to be? Well, this time the height is an x value, right? It's not a y value, it's an x value because things are kind of flipped sideways. And so how would you obtain that x value? Well, by plugging the y value into this function, right? So for example, if right now we're at, let's say maybe like 2.2 is the y value that we're at, and that's our radius, right? That's the length of this green line would be like 2.2. How would we then find this orange distance? Well, that's just the x coordinate. And how would you find the x coordinate if you know that y is equal to 2.2? Well, you would plug y is equal to 2.2 into this equation, and that would tell you the x coordinate, right? So because basically this, the parabola is what kind of determines where like the corner of the cylinder is, it's going to give you a relationship between x and y. And so if the radius is y, then the height is going to be whatever you get by plugging y into this equation. And so we can say that the height is equal to negative y squared plus 5y minus 4. And maybe just to mention one other thing. So why is it that we're integrating with respect to y here instead of with respect to x? So let me actually get rid of this for a second because I think it'll make it easier to see. So if I were to add, right, this, when we draw these, we're not generally drawing the thickness just because it kind of makes the picture a little more cluttered. But if we had a thickness to this, well, what direction would you be measuring the thickness in? It would be vertical, right? Like the change, the thickness is not horizontal, it's vertical. And so it would be delta y, which becomes dy when you turn it into the integral. So, okay, let me put the radius back in, and now we're ready to actually integrate this. So the volume is going to be equal to 2 pi times an integral from a to b of the radius times the height. Sorry, I lost my orange. There we are. dy. And so in this case, we want to be thinking about first, what is the smallest and the largest radius that makes sense? And so in this case, they're going to be y values, right? And so what's the very smallest y value where you could have a cylinder? Well, that would be at y is equal to 1, right? That's like that's where our shape starts essentially. And so the lower bound, and I'll put that in here, is going to be 1. So that's our a value. And so we're doing the integral from 1 to, and then what is the end? Well, the last place you could draw a cylinder would be at a height of 4. And then we have the radius is equal to y, and then the height was equal to all of this, negative y squared plus 5y minus 4. And then we're integrating with respect to y. Okay, so let's multiply this out and actually evaluate our integral. So we're going to have integral from 1 to 4 of negative y cubed plus 5y squared minus 4y. So again, I encourage you to pause this and try it yourself rather than sit there and feel bored as you watch me do fraction arithmetic, but you know, it's your choice. So we have negative y to the 4th over 4 plus, here we have 5 over 3 y cubed. And then here we have minus 4 over 2 y squared. And we're going to be evaluating at 4 and at 1. So this gives us, when we plug in 4, so 4 to the 4th power, that one I have to calculate. Sorry, 1 second. 4 to the 4th. So that is 256. So we have negative 256 over 4, which actually that's nice because then we'll be able to reduce that, right? And then the next part we have 5/3 times, so 4 cubed is equal to 64. And then we have, 4 halves is equal to 2. So we have minus 2, and then y squared is going to be 16. And then from that, we're going to subtract negative 1/4 plus 5/3 minus 2. Okay, so let's simplify things a little bit and see what we can combine here, and then we'll make a common denominator with whatever is left over. So 256 divided by 4 is 64, so this is negative 64. And then we have 64 times 5 in the numerator, and so that's going to be 320. And then we have minus 32, and then we have plus 1/4 minus 5/3, and then we have plus 2. Okay, so that's going to be 2 pi times, so the negative 64 minus 32 is going to give us negative 96, and then we're adding 2 to that as well, so that's going to be negative 94. And then we have 320 over 3 minus 5 over 3, so that's going to be 315 over 3. And then we have plus 1/4, and I think I got everything right. So we took care of the integers, and then we had the thirds, and now we have a fourth. Okay, so 315 over 3. So 315 is divisible by 3. So that's 105. So we have 2 pi times negative 94 plus 105 plus 1/4. And so that's going to be 2 pi times, so 105 minus 94. That gives us 11. So we have 11 plus 1/4. And so now we can make a common denominator. And so that's going to be 44 over 4 plus 1/4. And so that is 2 pi times 45 over 4. And we can reduce here the 2, right? So this will become over 2. And then at the end, we are left with just 45 pi over 2. So very, very similar to the way the other one worked when we were doing with respect to x. I think there's just something that's, for most people's brains, probably a little bit harder about picturing what's going on here. But you're still, the radius is just y to represent any height. I guess the word height is a little misleading to say here, but y to represent that the radius could happen at any y value. And then the height is determined by what that y value is with the relationship given by the function. Okay, so we're going to do another example very similar just to get a little more practice. So in this one, we're finding the volume of the solid obtained by revolving the region bounded by y is equal to x squared, x is equal to 0, and y is equal to 4, and we're revolving it again about the x-axis. So again, we're going to be integrating with respect to y. And so this time, this is our region. And we're taking this and we're revolving it around the x-axis. So we're going to have something that looks like this. And so what would this look like? Well, from the outside, notice that the outside edge is straight. So from the outside, this would actually just look kind of like a very smushed down cylinder. But then if you looked at the inside of it, the inside would be kind of like sloping in. It wouldn't have flat sides to it. So let's go ahead and draw a sample cylinder. And actually, before I do that, let me just quickly mention, this is something we'll talk more about in tomorrow's video. But in this one, you actually could use the washer method. So if you were going to use the washer method, you would have, your inner radius would be determined by x squared, and then the outer radius would just be 4. And so that would totally work, and you could do that. It's probably maybe a little easier in this situation, but I want to do the shell method just to get practice with that. Okay, so I'm just going to pick some random y value to draw my side of my cylinder, and then I'll draw one directly across from it. Maybe let me do that a little better so that it's more like here. And then we'll connect them with a circle, and there we have our cylinder. Okay, so again, the radius can be like any y value, right? So and this time actually starting at 0. So really we just want to let the radius be y. So it's free to be, anything from 0 all the way up to 4, any y value. So the radius is equal to y. And what is the height going to be? Well, again, now the height is determined by the function. But there's one issue here, which is that we were given this equation as y is equal to x squared, and we need to have it as a function of y instead of as a function of x. Because basically we want something that we can plug any y value into and figure out what that corresponding x value is, because the x value this time is the height. So how do we do that? Well, we just solve it for x, right? And so this would be x is equal to square root of y. Okay, so our height then is just square root of y. And again, I would encourage you to actually try some numbers and really kind of make sense of why that is. So like, for example, if we were to go to a y value of 4, so that would be like the very biggest cylinder you could get. That would be like all the way out here like this, if you were to do this cylinder. So if you're at a y value of 4 and you wanted to find the height, well, if you take the square root of 4, you get 2. And that's exactly what this height is, right? This is 2. So it makes sense. It works that when you pick your y value of where you're drawing your cylinder, that if you take the square root of that y value, that tells you the height of the cylinder. Okay, so that was really all that was kind of new about this one, was the fact that we had to, sometimes, like in the last one, you're given your function as a function of y. Other times you have to actually solve something in order to get it in terms of y. So again, we're going to be doing an integral from a to b of the radius times the height. Oops, I flipped these. Radius times the height dy. And so we already know our radius and our height, so the bounds this time, so what's the very smallest radius that makes sense? Well, that would be 0. So that's our A. And then what's the very biggest radius that would make sense? Well, that would be 4. So that's our B. So we're going to be doing the integral from 0 to 4 of, and the radius was y, and the height was square root of y, dy. So this one's going to be 2 pi times the integral from 0 to 4 of, so y, or square root of y, is the same as y to the 1/2. So if you multiply y times y to the 1/2, you get y to the 3/2. And so this one's going to be a lot easier to integrate. So the antiderivative is just going to be, so we add 1, and so that gives us y to the 5/2, and then we take the reciprocal, and so that's 2/5 y to the 5/2, and we're evaluating at 4 and at 0. And so when we plug in 4, we get 2/5 times, so 4 to the 5/2. And then when we plug in 0, we're just going to get 0, so we don't need to worry about that. So how can you make sense of 4 to the 5/2? Like, let's say you wanted to do this without a calculator. Well, you can think of 4 to the 5/2 in 2 different ways. So one thing you could think of it as, and let me even write this as kind of a side note. So 4 to the 5/2 is equal to the square root of 4 to the 5th, but it's also equal to the square root of 4 to the 5th. You can do it in either order. And so in most cases, it's easier to do the square root first, right? So the square root of 4 is 2, and then 2 to the 5th power is equal to 32. And so we have this. And then we can just multiply this stuff through. So we have 2 times 2 is 4. 4 times 32 is, that's a good question. What is that? 128. So we have 128 pi divided by 5. Okay, so next up, we're going to do a couple of examples that are going to be actually with respect to x again, but they're going to be a little trickier in a couple of ways. So this first one, we're going to find the volume of the solid obtained by revolving this region. So we have y is equal to x squared, so that's the curved bottom part, right? It would continue like that and be a parabola. And then we have y is equal to x, and that's the straight part, that's the line. And so we have this region here, this little sliver, and we're revolving it around the y-axis, so that's going to look like this. And we actually did this one, I believe, in our washers video. So what would this thing look like? Well, from the outside, it would look kind of like a bowl, like it would be a rounded shape, right? But then if you were to look on the inside, the sides would slant in a perfectly kind of like a cone way, right? It wouldn't have any curvature to it. It would be like these flat edges. So like I said, you could use the washer method here, but let's say you wanted to use the shell method. So let's go in and draw a sample shell. So how do we draw a sample shell? Again, we choose a height. And so this time the difference is that I don't want to make my height go all the way down like that. So why is that? Well, if I were to draw a cylinder that looked like this, that doesn't like fit within our shape, right? We want to make sure that the cylinders are actually kind of fitting in the shape, because together they're supposed to make the shape. And so the sample cylinder would actually just go between the two curves like that. So, and then we can do something symmetric over here. Is that symmetric? It looks about right. And connect them like this. And let me just kind of draw one more, and then I'll actually show you a video that's not with this exact one, but it's with a similar curve that can maybe help you visualize what's going on here. So you might have another cylinder out here like this. So this time it's like, because the shape is just really different, the cylinders are kind of, they're all pretty short and they're kind of staggered in a way. So let me just show you this quick video clip. It's not the exact same function. So this one I think is square root of x and x squared instead of, so the bottom curve is the same, but the top curve, instead of being a straight line, it's also curved. But it's a pretty similar shape. And so what this video is going to show is that if you were to kind of just draw on one of these heights and revolve it around, that would give you one of the cylinders, right? And so then if you take the shape and you divide the entire thing, let's wait till they get there. Sorry, they're probably talking about something. But if we now take the shape and divide it all into these different kind of vertical slices, well, then when you revolve that around, you get a bunch of cylinders, right? That all kind of nest within each other. And this isn't going all the way around, but it's showing part of it. And so when we complete this, we can see that we have this, like, see how the edges are kind of jagged? So it's not the exact shape, but it's this approximation of it. And then in a moment, what they'll do is they'll actually show they'll smooth out the sides and show, you know, what the actual volume would look like. So that's what the edges smooth, but you can see that with the approximation, it's pretty good. And so that's what you want to picture. In this case, you want to picture like these thin kind of shells like we saw in this one that are nesting together like this. Okay, so let's do this example. So what would sorry, let me just get rid of this orange one. Okay, so what would be the radius in this case? Well, again, now we're going to be integrating with respect to x, so we want everything to be in terms of x. So in this case, the radius is just equal to x again, right? Because whatever x value you're at, you know, that's the radius that you have in your cylinder, and then we want to include every possible x value to get all of those cylinders. But the height, now the height is going to be a little trickier because it's not just one function, right? So how would you find this orange distance? Well, you would subtract these two functions, right? So if you just did, let me maybe go in here and draw something that I'll take out afterwards to make it less complicated. So if you did a distance of x, so that would be using just the top function, which is y is equal to x, that would be this distance. And then if you take the, I'm trying to think what color I didn't use yet. Maybe let's use this. If you then wanted to subtract out this bottom part, so this part that I just highlighted in green, that distance would be x squared. And so if you do the purple distance, which is x, minus the green distance, which is x squared, that will give you what we want, which is this orange distance. So if you do the top function minus the bottom function, basically that's going to give you your height. And this is why drawing the picture is so important, because you never want to just make an assumption about what the height is going to be or what the radius is going to be. You really want to see it for yourself in a picture. So let me write that back in again. So our height was x minus x squared. And what are our bounds going to be? Well, the smallest place, the smallest x value that will have a radius is at A, and the biggest x value that will have a radius is at B, which is 1. So we have 0 to 1. So now we're going to have the volume is equal to 2 pi times the integral from A to B of the radius times the height, and we're integrating with respect to x. And so that's going to be 2 pi times the integral, like we just said, from 0 to 1 of, so the radius, I flipped them again, I keep doing that. So the radius is going to just be x, and then the height is going to be x minus x squared. Okay, so that's going to simplify to 2 pi times the integral from 0 to 1 of x squared minus x cubed dx. Okay, so our antiderivative is going to be 1/3 x cubed, or we could write it as x cubed over 3, minus x to the 4th over 4, and we're evaluating at 1 and at 0, which is nice because those are like the easiest numbers to plug in. So when we plug in 1, we're just going to get 1/3 minus 1/4. And we want to make a common denominator. So the common denominator would be 12. So we have 4/12 minus 3/12. And so that's going to give us a total of 2 pi times 1/12. And so that's going to simplify to pi/6. So that is our volume. Okay, so very last example. This one is going to be the trickiest, and this one is going to involve revolving around an axis that is not the x or y axis. So we have the region, and I left something out here. So it's the region bounded by this parabola, and then we should also say, and y is equal to 0. So this, again, kind of little top of a parabola. We are going to revolve that now around the line y is equal to 2. So what that means is you can almost kind of like imagine, it's almost like you just took your whole kind of coordinate system and shifted it. So now you can almost kind of like forget about the y-axis and just like pretend that this line y is equal to 2, pretend that's the y-axis and think about what this would look like. So basically what would happen is this would just end up being reflected over here like this, and then it would be this round shape. Again, it would be like kind of like the bagel or donut shape, except for that it won't actually have a hole in the middle. So it's like, I don't know if you've ever had a donut or bagel where it's like so full that it doesn't actually have a hole in the middle. It would look like that. Okay, so now when we go and find the radius and the height, we'll see that there's a little bit more kind of trickiness going on. So I'm going to start by drawing a sample cylinder. So that looks like that. Okay, so the radius. So the important thing to remember is that the radius is literally the radius, right? It's the distance from the line y is equal to 2 to the edge of this cylinder. So I'm going to start by telling you why the radius is not just x in this case. So let's look at where we drew the cylinder. So you might estimate that based on kind of where we drew this, it looks like x is probably equal to about, let's say 2.6, right? So this whole distance here, this would be x. So again, if you want to get really concrete, think of it as being 2.6, right? X in this case is 2.6. X is literally the x value that we're at when we're drawing this cylinder. And that's not equal to the radius. So it was in this example. Let's go back and look at it. So why was x the same as the radius in this example? Well, because basically we were revolving around the y-axis. The axis that you're revolving around is where you're measuring the radius from. Right? And so if you're revolving around x is equal to 0, which is the y-axis, well then the distance from that axis of rotation to the edge of the cylinder is just going to be the same as the x coordinate. But in this case, because we're not revolving around the y-axis anymore, it just doesn't make sense to say that the radius is x. So x is all the way this whole purple thing. So how would we find this green distance? Well, we need to do some subtraction. So if this purple distance is x, what would we need to subtract in order to figure out what this green distance is? Well, we would need to just subtract 2. Right? So if we did, so let me write that down. The radius is going to be equal to not x, but x minus 2. And that's again because x is literally the x coordinate of where you have the cylinder, right? And that is not accurate for the radius. And so how do you, if we have this whole distance in purple and we want this shorter distance in green, how can we get it? Well, we just want to subtract away this extra space. Basically, everything from 0 to 2 is this extra space that isn't contributing anything to the radius. Because we're revolving around the line y is equal to 2, all this extra space at the beginning is not contributing to the radius. And so that's why we need to subtract it out. I would be very hesitant to try to memorize some rule like, oh, you just do x minus, whatever the number is, because depending on where this axis is, that's actually not always going to be the case. In some cases, you actually might need to add something. So I would really, really recommend drawing a picture and just like looking at geometry and just thinking about what do I need to add or subtract to figure out what that specific green line that I drew, how to find that distance using just addition or subtraction. Okay, so what is our height going to be? Well, this is the thing that I think maybe is a little tricky. So to find the height, that you actually still would just plug in whatever your x coordinate is into your function, right? So again, let's think about looking at the x value of 2.6. So let's say that we're at an x value here of 2.6. So what would the radius be in that case? Well, the radius would just be 0.6, right? Because we would subtract out the 2. But how would you find this height? Well, you would just plug 2.6 into the function, right? Because forgetting about everything else, forgetting about the radius, just saying like, we're just trying to find this orange distance, if all you're trying to do is find this orange distance, well, how do you always find a distance vertically? You find it by plugging an x value into whatever the function is. And so in this case, the function is this. And so that is going to be our height. So the height is going to be negative x squared plus 6x minus 8. So I know there's something kind of weird about that. Like I can see thinking that maybe the height, like you shouldn't just be plugging in x, you should be plugging in x minus 2. But again, like try some numbers. I really, really encourage if you're having trouble with this, like pick a concrete number and actually literally figure out what the radius and height are for that concrete number. And I think that will really help you understand how to do this in general. Okay, so let's now set up our integral. So I hope this doesn't get too confusing with my color coding. Maybe I'll use different colors now for A and B. So for A, we're just again looking for what's the very smallest x value that it makes sense to plug into this. So what is the smallest x value that makes sense here? Well, it would actually be 2, right? Because that's where we like think about to draw the smallest possible cylinder. That's my advice is kind of draw like this like little tiny miniature cylinder and think about, okay, where, what's the x value where I'm drawing that? And in this case, it would be 2. So the lower bound is 2. And then where's the very biggest place you would draw the cylinder? Well, that would be at 4 in this case. So that's our b value. Okay, so let's set this up. So the volume is going to be equal to 2 pi times the integral from a to b of the radius times the height dx. And so this is going to be 2 pi times the integral from, so we said 2 to 4. 2 is our lower bound and 4 is our upper bound. And our radius is x minus 2. And our height is negative x squared plus 6x minus 8 dx. And so now we just have to multiply in this up this polynomial and take our antiderivative. So let's see, we get negative x cubed plus 6x squared minus 6x. And by the way, this is another example that I would really encourage you to pause it and kind of see if you can take it from here, because I think it'll be pretty boring for you to watch me do this. And then we have plus 2x squared minus 12x plus 12, right? Because we have a negative times a positive. And so if we combine our like terms, we have negative x cubed, so that's our cubes. What do we have for squareds? Well, we have 6x squared and 2x squared, so together that gives us 8x squared. And then we have negative 6x, negative 12x, so together that gives us negative 18x. And then we just have one constant, which was plus 12. Okay, so our antiderivative for the first part is going to be negative x to the 4th over 4. And then we have 8 over 3 times x cubed. And then we have 18 over 2 times x squared. And then we have 12x, and we're evaluating at 4 and at 2. So let's start plugging some stuff in. So for the first one, we have negative, so this is actually very similar to the last one. So negative 256 over 4. And then we have 8/3, which is being multiplied with 64. And then 18 over 2 is 9, and we're multiplying that with 16. And then we have 12 times 4, which is 48. I'll just write that out. And then from that, we're subtracting. Now we have to plug in 2. So plugging in 2 is going to give us negative, so 2 to the 4th is 16. So we have negative 16 over 4 plus 8/3 times 8 minus 9 times 4 plus 2 times 12 is 24. And by the way, I mentioned this at some point, but if you ever see me make an arithmetic error or any other kind of error in a video, feel free to either send me an email or maybe just even comment on the video, and that way other people will be able to see your comment so that, you know, they'll know that there is a mistake if there is one. So negative 256 over 4 is negative 64. And then we have 8 times 64 is 512 over 3. And then we have 9 times 16, which is negative 144. And we have plus 48. And now we have plus, so 16 over 4 is 4. And now we have minus 64 over 3. And now we have plus 36. And now we have minus 24. Okay, so a bunch of numbers to combine here. Let's start by combining the integers. So if we add together negative 64 minus 144 plus 48 plus 4 plus 36 minus 24 altogether, that gives us negative 144. And the next thing we want to do is combine these things that are over 3. And so we have 512 minus 64, and that gives us 448. And let's see, is 448 divisible by 3? It is not. Okay, so now we want to make a common denominator. So our denominator in this case will be thirds. So we want to multiply negative 144 by 3, and that gives us negative 432 over 3 plus 448 over 3. And it's always kind of a relief when you can tell that the answer is going to come out positive. So if your answer ever comes out negative, you definitely did something wrong, because these should not be negative. It's a volume. And so that simplifies to 16 over 3. And so now our final answer is going to be 32 pi over 3. So that one was kind of a doozy. But yeah, like again, can't say it enough. Best thing you can do is draw these and really be comfortable with actually testing out some numbers if you're struggling to figure out what the radius and the height are. So in the next video, we're going to be doing more practice with volumes, and we're going to be kind of looking at problems where you're not specifically instructed as to whether you should use, which method you should use. And so we'll talk about how you can decide which method to use. And in many cases, either method will work, and we'll kind of talk about the pros and cons of all the different methods. So I'll see you next time.